Okay, so hello everyone and welcome to the week 7 lecture for the materials selection and design. Today's topic is going to be resources, reserves, and materials. First, dependence on non-renewable materials is one of the main issue we have nowadays. Modern concerns for the sustainability are emphasizing the use of the materials that are renewable in nature. So interestingly, that the use of the renewable materials was commonplace for the humans as recently as 300 years ago. Such a materials consist of the wood, stone, leather, bones, and natural fibers. The non-renewables such as the iron or the copper were used in such low volumes uh, that they also can be considered to be inexhaustible. The impact of human activity on the status of the environment and the ability of the planet to support the humans challenged by first the population growth and second by the increased per capita material consumption. Where do materials come from? From the periodic table, there are 92 naturally occurring elements from which the materials can be made. Many of the engineering purposes they require metals, but the metals are commonly sourced from the naturally occurring ores, oxide, sulfate, or the carbonate and extra, and are often mixed with the other metals. From below, the eight most abundant elements are going to be the oxygen, the silicon, the aluminum, the iron, the calcium, the potassium, the magnesium, and the titanium, and these account for about 98% of the abundance of all elements. So how do these relate to the most common engineering materials? Can you actually give an idea about the steel, how the glass, the concrete, and the bricks? So the metal contents is an ore called the ore grade G, and this is defined as the metric tons of the metal per metric tons uh, of ore mined. From this, the cost of the metal extraction is going to be approximated by the value for the CM, or the cost in kilograms in dollar. It's going to be equal to 10 divided by G. However, this improved by selecting the ores from the regions where the metals have been naturally concentrated. This also ignores the effects of the geopolitics on the supply and demand. The distribution of the minerals across the earth have been determined by first the volcanism, where the volcanic activity separated minerals according to the melting point, the erosion, where the wind or the water wear minerals down, enable them to be separated according to the density or by the gravity, or the water that separates and distributes the minerals according to their solubility, where the pH matters too, which is the acidity and the alkalinity. And we have the organisms or the concretes minerals according to natural processes like the metabolic or otherwise. Such processes tends to be very slow, and so the collection of the minerals can be exhausted in a finite timescales. The mankind depended on resources that are materials, energy, and water. So let's start with the materials. In 2012, 10 billion metric tons of engineering materials are consumed annually, and this approximately about 1.5 metric tons per annum per person. This still accounts for about 10 times the amount of all the other metals combined, led by the aluminum and alloys. The polymers are roughly equal to the aluminum, and the concrete exceeds the steel by a factor of 10. The construction timber also exceeds the steel. The glass and the bricks are similar to the aluminum and the polymers in the amount of consumption. Now we come to the energy, where the energy is an inseparable form of the materials due to the needs for the energy to obtain the materials via the extraction, the refinements, the manufacturing, the logistic disposal, and extra. Now in 2012, The global consumption of the energy was about 500 extra joule per annum, which is one extra joule is about 10 up to the power 18 joules, and making the materials consume about 21% of the annual energy demand. This also corresponds to about 20% of the global CO2 emission. While there are sources of the energy, like the fossil fuel combustions or the solar harvesting, the energy nearly always must be transformed to be useful. And this always results in the energy losses and typically with the generation of the low-grade heat. The conservation of the thermal-mechanical energy is limited by the Carnot efficiency, where the Carnot efficiency is going to be equal 1 minus the temperature out divided by temperature in. So for a given temperature, for a given out temperature, the efficiency improve with an increased input temperature, and therefore the development of the temperature-resistant materials can lead to the improvement of the Carnot efficiency. The industrial processes involve many of the energy conversion steps, forming chains. When these chains are going to relate to the production of the materials, the associated energy expense is going to be called the inputted energy. And it is not recoverable energy, but it's going to be a measure of the energy inputted to achieve the current state of the material. So, for example, the change is free energy between the iron oxides and the iron itself is going to be about 6.1 megajoule per kilograms. In a principle, this could be recovered if the freon or the iron itself was oxidized back to the freon oxides under perfect conditions. Due to the inefficiencies, the actual energy required to make the freon is going to be about 18 megajoule, and his 18 megajoule per kilogram is going to be the inputted energy of the iron. Now we're coming to the water. Water is abundant, about 97% of the water is salt water, and only 20% of what remains is going to be frozen as an ice, and then we're going to have only 1% as a water. So, in principle, the water is going to be renewable, but is dependent upon the global ecosystem. The agriculture consumes about 65% of the fresh water, and industry consumes about 10%. While the consumption of the water for the production of the materials is not a major concern, the emergence of the biomaterials may lead to the increase of the water demand. So we have three different terms about the energy, like the reserves, the resources, and the resource life. So the minerals that provide the materials used in the engineering or technology are almost entirely sourced directly from the earth. The reserve is defined as a known mineral deposit that can be accessed legally and through a sufficient technology that to be commercially feasible. A reserve is not a total amount of the mineral, nor the sum of all the reserves, the total abundance of the minerals. A resource, is going to be defined as the real abundance of the mineral, and it includes the measures of the current or the predicted reserves, but is going to be an estimate by the nature. We have a complex relationship exists between the reserve and the resources, but typically drives for the increasing reserves are going to be first, increase of the commodity price, second, the improved extraction technology, third, the decreased production cost, and the favorable legislations and the increased prospecting, and finally the increase of the export demand. So usually the resources are going to be critical, or the criticality of the resources is going to depend on the time to exhaustion. So the availability of the commodity depends upon the balance between the supply and demand. While in principle, market forces attend to the fluctuations in this balance. The ability of the supply chain to respond is critical. For example, can a new reserve or an improved extraction process can be to be found and utilized in times to address the spike in demand or not? Also, what we can see nowadays about what we have in the tariff wars between China and United States, and actually we can see that there are some of the minerals that um, dominated by China. So this is one of the things which can tell you about what is the conflict between the supply side and the demand side. So what's happened when resources approaches the exhaustion? Time of the exhaustion is used to predict the life remaining in resources. This can be predicted based on the current rates of the production and this reserve size, which is going to be called the static index, or with the growth rate factor in the dynamic index. While these suggest that the lifetime can be predicted, they instead indicates the balance of the supply and demands and the market exceptions of the lifetime. A deviation from this expectation provides an incentive for the interventions. So, riskality and market balance and breakdown. So, the scarcity of the commodity occurs when supply gets outstripped by the demands and the market cannot respond effectively. In this case, the price of the commodity is no longer going to be determined by its production and distribution costs. So, for resources that are widely available at high grade, the supply-demand balance is going to be easily maintained by the supply chain. However, for those commodities that are not widely available, supply chain becomes constrained and are going to be correspondingly vulnerable to the influence that are going to be separate from the extraction and distribution. The example will include the government policies, the cartels, the wars, the conflicts, and the natural disasters. An example for that is in oil. Supply chain is resistance to these influences when comprises a wide distribution of the procedure and distribution. So, what are the realistic indicators of the criticality? So, the rate of discovery, the rate of the production, and the corresponding of the commodity price are indicates below. Several of the important details are indicated, including there is a lag of the time between the rate of discovery of the reserves and the rate of the production from it. Also, initially, the rate of the discovery is going to be higher than the rate of the production, leading to the reduction and the subsequent stabilization of the price at the low level. The rate of the discovery will slow, leading to the peak and then the decline, where the rich grades are going to be mined professionally. Likewise, the rates of the production also going to be peaks and decline. Eventually, the price begins to increase, and this may persist if the resources are going to be depleted or may initiate a new round of the discovery. Well, obviously that this diagram is old, it's from 2008, but in general, this will show you the relationship between the discovery, the discovery curve is shown at the red smooth line, and the oil production rate is the black line, and we have also the oil prices in the dashed blue line. So you can see that the real relationship between the discovery and the production rates and the price is going to be complex, but the general behavior is going to be apparent. Usually when you get to have a crisis, the oil price will be jump, like what we have in the case of the energy prices of 1978, which actually started the increase during the 1973 oil embargo on the West. So you can see that the price jumped from about $20 or less up to $60 and then continued to increase to $100 back in 1978, which at that time worth in something like $200 today. The peak price reached to the oil was the spike of 2008 due to the global recession. And after that, the price dropped down to the average of 120 for a few years, and then it's dropped down to 60. Then now it's on the average of $74 due to many of the geopolitical reasons and uh, uh, for example, the trade war and other stuff. So once again, there is nothing constant, but still, that's what we have in the case of the criticality of the prices. So the strategic or the critical materials that we have in life. So actually, I going to show you in the class a post that I made on LinkedIn about this issue. So the resources-based underpinnings, many of the materials is going to be very large and well distributed. Hence, a supply and the price of such materials is going to be predictable. Like when we're going to talk about the copper or the iron ore or whatever things. And during example, including the iron and the coal for example, the steel and the epoxy for the aluminium. However, the materials that have a specific value either by themselves or through the contribution to a key industries, but those resources are going to be highly localized or highly constrained geopolitically again, identified as a strategic or the critical minerals. Example are provided in the following table and many relates to the emerging technologies. Okay, so the following table actually shows the list of the critical strategic materials and their critical application and the principal global sources for them. Now, once again, I will ask you to make your own research to find actually what are the materials, different materials. I mean, I would like you actually to make something like a research to update this table because this table is quite old. Okay, now we're going to have a look on the materials energy carbon triangle. So as resources become depleted commodity, the prices will increase such that more reserves become available. However, such reserves are going to be increasingly difficult to utilize. Hence, more energy is going to be required and the materials become increasingly energy intensive. If this energy is going to be provided by fossil fuel, then resulting materials are going to be correspondingly increasingly carbon intensive also. On the other hand, energy may be provided renewable or with a low carbon emission. At present, such energy resources are going to be energetically dilute and compared with the fossil fuel. And so they will tend to be a very large to compensate, and hence the energy solution are going to be material intensive. The result is going to be close interdependence between the energy, the carbon emission, and the energy which needs to be considered carefully within the material selection and the engineering design process. So we talked about the material life cycle earlier, but now we're going to have more review on it. So the material life cycle is an interpretation from the study life science, with the application to materials such as the flesh and the bones of the products relied upon by the society. The material life cycle consists of the main assessments of the material's interaction with the environment during the various stages of its life, from the extraction to manufacturing to use and finally disposal. With a growing emphasis on the greater responsibility from the reducing of the environmental impact, engineering design and material selection must be increasingly consider the environmental impact of each stage. These concepts will be developed further in the later lectures. So the important readings for this lecture was the Materials and the Environmental second edition for 2013 by M.M. Ashby, and the chapter was chapter number 2. So thank you for your listening, and we'll get more discussion in the class.